All right, so you've got exams on the horizon and Chapter 8 is on the list. Well, you're in the right place. We're going to do a super fast, laser-focused review of transition and intertransition elements, hitting all the key concepts you absolutely have to know. No fluff, let's dive in.
So, here's the game plan for today. First, we'll get to know what these transition elements really are. Then, we'll tackle the electron configurations, the stuff that always trips people up. After that, we're going to spotlight a couple of chemical superstars, check out their most famous properties, and then we'll finish up with a quick look at those F-block elements. Sound good? Let's go.
Okay, Section 1. Before we jump into all the complicated stuff, we need to nail down the basics, and that starts with a really simple question. What actually is a transition element?
Okay, so the official definition all comes down to this one little phrase, an incomplete D subshell. Seriously, that's it. That one characteristic is the key to their entire personality. It's what makes them so different from the elements in the S block and P block, and it's what unlocks all of their really cool, unique chemistry.
And just look at where they live on the periodic table, right smack in the middle. They literally form a bridge between the superreactive metals on the left and the nonmetals over on the right. And that means their properties, things like reactivity, are kind of in between, which is what makes them so incredibly versatile.
All right, now for the part that can be a little tricky, their electronic structure. We're going to look at the rules they follow, but honestly, what's more important are the exceptions. Because let's face it, on an exam, the exceptions are where the real points are.
Pay attention to this slide, because this is the golden rule. It's the key that unlocks all the exceptions we're about to talk about. It's a fundamental principle of chemistry. Nature just loves stability. And for atoms, that means having a d orbital that is either perfectly half full or completely full. You got to burn this idea into your brain.
Which brings us to this question, and I guarantee you've seen this on a practice test or in a textbook. It's a classic. Why on earth do chromium and copper have these weird, anomalous electronic configurations? Well, the answer goes right back to that principle of extra stability we just talked about.
And this table here shows you exactly what's going on. Just look at the observed configuration column. For chromium, you'd expect it to be 3d4, but nope. An electron actually hops over from the 4s orbital to create that super stable half-filled 3d5 subshell. And copper does the exact same thing to get that ultra-stable, completely filled 3d10 subshell. See, it's all about chasing that extra stability. So here you have it. This is basically an exam alert. These two configurations, you just have to memorize them. There's no way around it. They are the classic exceptions that actually prove the rule of stability. Know them cold. Okay, let's talk about a couple of key trends you need to know. First up, atomic size. So as you move from left to right across the series, you're adding more protons to the nucleus, right? So think of it like upgrading the magnet in the center of the atom. It gets stronger and pulls all those electrons in just a little bit tighter. That's why the atom gradually shrinks. Now, the effect isn't huge, but the trend is definitely a slow, steady decrease in size.
And what about the energy it takes to rip an electron away, the ionization enthalpy? Well, once again, they're right in the middle. It's way harder to steal an electron from them compared to the S-block metals, but it's easier than from the P-block nonmetals. It's this sort of Goldilocks energy level that makes them so flexible, able to form both ionic and covalent bonds.
Okay, time to meet the rock stars of the transition metals, potassium permanganate and potassium dichromate. These are the MVPs of redox reactions, for sure. For this review, we're going to put potassium permanganate under the microscope, since its reactions are classic exam questions.
So, how do we make that famous, vivid purple solution? It's actually a two-step dance. First, you take manganese dioxide and oxidize it to create this dark green stuff, potassium manganate. Then comes the really cool part, a process called disproportionation. Basically, in this reaction, the manganese atoms in that green compound start reacting with themselves. Some get oxidized, some get reduced, all at the same time. And it's this weird internal shuffle that transforms the green solution into that deep purple potassium permanganate we all know. So the big takeaway, potassium permanganate is a chemical bully, especially when it's in an acidic solution. It is an incredibly strong oxidizing agent, which just means it aggressively rips electrons away from other things. And these examples on the slide, this is pure exam fodder. You should definitely know how it yanks electrons from iron, turning it from a +2 to a +3 state, or how it turns iodide ions into iodine. And this is really the bottom line for this whole section. Just remember, these compounds are the heavyweights of redox reactions. Their whole deal is being a powerful oxidizing agent.
That's why they're so important everywhere, from industry to the chem lab. So when you see KMNO4 in an equation, your first thought should always be, okay, what is it about to oxidize?
Okay, let's move on. Beyond just those two compounds, the transition elements as a whole family share some really cool and distinctive properties. Let's talk about their amazing colors, their magnetic behavior, and, where we actually use this stuff in the real world.
Have you ever wondered why so many of these compounds have these incredible vivid colors? I mean, think about it. Copper sulfate is bright blue, potassium permanganate is that deep purple. It's not a coincidence. It all goes back to those incomplete d orbitals. Electrons can actually jump between these d orbitals. It's called a d-d transition. And to make that jump, they have to absorb light of a very specific color. The color we end up seeing is just whatever light is left over. It's like the opposite of the color they absorbed.
And it's not just their color. That same electron setup is also why so many of them are magnetic. So what's the deal with that?
You ready for the secret? It all boils down to one single thing: unpaired electrons. That's it. If an atom has lonely, unpaired electrons spinning around in its d orbitals, it's going to be paramagnetic, meaning it gets pulled into a magnetic field. But if all of its electrons are neatly paired up, it's diamagnetic, and it actually gets weakly pushed away. It really is that simple.
And look, this isn't just stuff that happens in a textbook. Take potassium permanganate again. It has a ton of real-world uses. It's a workhorse in labs for measuring other chemicals, it's used as an antiseptic, and in organic chemistry, it's used to test for certain kinds of bonds. That powerful oxidizing ability makes it super useful.
All right, for our last section, we're going to go one level deeper into the periodic table. We've talked about the D block, but what about those two mysterious rows that always sit at the very bottom? It's time for a quick look at the F block, also known as the inner transition elements.
So, what's their defining feature? Well, while the regular transition metals are filling up their d orbitals, these guys, the inner transition elements, are busy filling up their f orbitals. And because these f orbitals are buried 2 whole energy levels deep inside the atom, their chemistry can be even more subtle and complex.
And that complexity has some really interesting effects. For one, their ionization energies are all over the place. There's no smooth trend. But more importantly, as you move across the first series, the lanthanoids, the atoms actually shrink more than you'd expect. This is a huge concept called the lanthanoid contraction, and you should definitely remember that term. Because they all end up being so similar in size, they're incredibly difficult to separate from each other, which is a major headache for chemists.
And that brings us to our final thought. These elements, with their mind-bendingly complex orbitals and unique properties, are already at the heart of technologies like powerful magnets, lasers, and all sorts of electronics. So the big question is, as we get better at understanding them, what incredible new technologies might they unlock? What's the next chapter for the F block?